So we shall wait 1 more minute. After that, um, we'll start. Okay, let us start. Let me introduce today's speaker, Dr. Sarfraz Hussain. He's a professor in Reva University, Bangalore, and he and I have done quite a few this kind of webinars, workshop, face-to-face workshop. So he is very good in analog design, and he also uses open source tools. And I'll invite him to take over today's session and start the analog design uh, methodologies.
Yeah,
Over to you, Dr. Sarfraz.
thank you so much, sir. So thank you, Alok sir, for the introduction. And I welcome you all. So as Alok sir said, so we had done these kind of workshops earlier as well. Like we had, so basically Alok sir has taken up the digital part and I have taken up the analog part. And for the analog design, as you know, most of you might be using the commercial tools such as the Cadence, Virtuoso. And what we are trying to do here is that make use of the open source tools. Now, for the digital, you may have heard of OpenLane and other tools, but for analog, most of us are not utilizing those tools. And mostly whatever tools we are using are the spice tools such as the LT spice, P spice, and other spice tools such as the H spice. So mostly those tools are used to do only the circuit simulation. Now, the advantage of the EDA tools as of now is to like do the complete flow right from the schematic till the layout and up to the GDS2, that is the graphical data stream generation, which will go to the fabrication lab. So we are here to use, like here we'll be basically using two tools. That is, one is electric VLSI, which will be used mostly, we'll work on that one. And LT Spice will be basically using for the simulation purpose. Just to observe the output, we'll be using the LT Spice tool. And there are multiple tools basically which we can see. And there is some magic tool is also there for doing the layout. So it all depends upon you which tool you want to use. And as per my experience, so I prefer the electric VLSI tool because in this particular tool, you can have the complete flow. So with this, let me begin this one. And I welcome you all. Thank you all for joining. And let me just share the PPT for today. And there I'll show how to use these open source tools. So to get you guys familiarized with the tools and all, how to use those, and about the Global Foundries 180 nanometer technology also, how we can use that PDK in our design as well. So let me just share that. Okay. So I suppose this PPT is visible. So let me just start. So in any instance, if you have any queries, just let me know and I'll be happy to help you out. So my name is Dr. Sarfraz Sen. So I'm an IEEE senior member, IST Life member. I was also a young researcher awardee and a Vishweshwara PhD fellow. I've been an Exicom member for the SEDA and CS. And let me start this topic with the session named as analog circuit design using the open source tools. So first of all, we'll cover this part, that is understanding the VLSI design flow, which is very, very important because whenever we are designing something, so we should know the flow, like where to start, what will be our starting point, and how we'll go forward with it. So let me tell you about the analog IC design flow. So starting with this one, so here is the thing how you can proceed and in like what duration you will be able to complete that particular designing part. So at first, what we need to do is to have a concept or an idea, like for example, an application. And for that one, let's say we want to use a ADC. Okay, we want to connect an ADC with a temperature sensor and need to generate the data out of a temperature sensor. So for that one, we need a ADC. So like that, we have to have a concept or an idea. That means what we are trying to achieve here, whether we are going to make a sensor, whether we are going to make a amplifier, or whether we are going to create a ADC, that is analog to digital converter. So there are a lot of analog designs that we can actually do. So we have to identify that one. And from the identification part, after identification, we have to give some specifications. So in this specification, basically, what should be the delay, what should be the power consumption, what should be the gain. So all these power requirements, the timing requirements, and the area requirements. So all those things comes under the specs basically. So what specifications we are taking into. So basically these things like specification, concept, implementation, and the architectural part is basically like taken up by some system engineer or a manager. So they will actually give these things. So this I'm talking about what usually there is in a particular industry. So we have system engineers, we have design engineers, layout engineers, and finally it goes to the fab, and there is a test and verification engineer, which actually works for the test and verification. Now, the first phase is to start with a concept, have a specification, and then go for a architecture. What kind of architecture you're planning to? Let's say, for example, let's start with an open design. So if you are starting with an op-amp design, so whether it is a two-stage op-amp design, whether it is a three-stage or four-stage, so that we need to identify. Then again, what will be the VDD, what will be the power constants, what will be the gain. So all those things will come under the specification part and architecture part. So this usually takes around 1 to 2 weeks. So if you are good in having this one like specifications, if you can observe or identify quickly, then you can actually finish it in 1 week basically. Then next is the schematic design and simulation. So once your architecture is final, so we can go for the schematic design and do some simulation. So usually this part, that is the schematic design and simulation, takes around 3 to 6 weeks, and that usually is taken up by the analog designer. But here, since we are mentoring, so you can actually go for op-amp design, and you can do a schematic design of an op-amp. Then you can do the simulations such as for, let's say, for the gain, for the pace, for the constants like UGB, unity gain bandwidth. So all those things we need to do the simulation, and that takes around 3 to 6 weeks. Then after that is completed, so then there is a layout generation. So once your schematic is ready, you have done the basic simulations, then we can generate the layout. So we have to make the layout of that op-amp circuit. Then we do the DRC analysis. So DRC is basically stands for design rule check. Now for each of the designs that we actually do, so it's based upon the technology that we are using. And with that technology, we have a rule called as the lambda rule, which actually says what should be the distance between a metal one and a metal two layer, or what should be the minimum distance between a metal and a polysilicon layer. So these things or these rules are stored in our technology file, and that is read by this DRC simulator tool. And this is done just to check whether we are satisfying the minimum design rules of mass. Now, after the design rule check, the next thing that we do is layout versus schematic. So whatever layout we have generated, whether it is matching with the schematic or not, so that also we need to check. It should not be that in the layout we are using some different thing, and in the schematic we are using some different thing, and the connections should also match. So that is why this matching of the layout and the schematic plays a very important role. Then after that, there is antenna rule. So if you're using any kind of antenna, so there it can, or if you're not using this, you can directly go to the PEX. Now, what it does is in a PEX, we are basically doing a parasitic extraction. So this PEX means parasitic extraction basically. Now, what are these parasitics? So as we already know what is a parasitics, so parasites are what? So usually the general term like parasites. So they feed on others, right? They depend upon others. So they absorb the energy from others. So these are parasites. And because of these parasites, our system becomes slow, right? So just you can have an analogy with the actual parasites that we have and the parasites we are talking about in case of a circuit design. So we need to extract these parasitics because these parasitics are basically resistors or the capacitors attached with the wires. So these metal wires that we are using or polysilicon wires that we are using, so based on the length of these wires, there will be some additional resistance or a capacitance, which we call as a parasitic resistance or parasitic capacitance. Now, after extracting these parasites, so this usually can be covered in 1 to 3 weeks. So usually this layout part actually takes around 2 to 3 weeks because it takes a lot of time depending upon the design we are making. So if it is a small design, let's say around 10 to 20 transistors, so it will not take much. But if your design is a larger one, then this particular layout portion will take a lot of time. Now, once this is done, then we do the post layout simulation. So what happens in the post layout simulation is after doing the layout, okay. So after doing the layout, so there will be some parasitics. Now, based on this parasitics, our outputs will change. So there may be a change in our gain, there may be a change in our delay. So there are a lot of things, and maybe our power consumption will also increase after the post layout. So that is why post layout simulation is important. That after layout, what are the additional parameters? Like after adding the parasitic, how my circuit is going to behave. So this post layout simulation does not take much of the time. So within just within a week, actually we can complete this post layout simulation. And after this post layout simulation is completed, then we do go for the floor planning. So in the floor planning, we have a complete description of the chip, how much area has been given to us, and how we are going to place our design onto the particular area that we have been given. Now, once we place our design, we need to do a dummy filling. So wherever there is a space, so we need to fill it up and we need to do a proper connection through the routing process. Now, after that is done, we go for again the DRC and LVS check. Okay, so that after the floor planning, still our we get the result basically. So after that, after this floor planning also, we do the DRC and LVS check just to check that our design is working fine along with the floor planning. So basically in the floor planning, we put some pins. Okay, so we put some tabs and therefore we need to do the DRC again just to have a cross check. That's it. Now after that, what we do is after completion of this one, we export the file in the name as .gds2. So the file that is saved is as GDS2 file, and GDS stands for the graphic data stream. So it is a combination of the data stream. So like all the, you can say, data that is required to generate a layout. So all those are stored in a text file, you can say. Now, after that file is generated, we send it to the fabrication lab. So usually the fabrication takes around 2 to 3 months, which is near about 10 to 14 weeks. So it takes a lot of time. So within 2 to 3 months, we can actually have the fabrication. So the up to the GDS2 part, we don't like we can do within 3 months to 4 months. We can actually complete the whole designing part up to GDS2 file generation. So that can be completed within 2 to 3 months. We can actually complete the design and the generation of GDS2 file. And after that, post generation of that file, we need another 3 months to 4 months for the physical fabrication. Then after the fabrication is done, then actually in the fabrication, we also need to get some time also because these fabrication labs and all, so they have a specific time given to us that you have to submit your design by this deadline. If we don't submit by that deadline, again it increases. So that is why we say that this particular 2 to 3 months can increase or decrease based on the timeline that has been given by the fabrication lab. So this usually differs somewhat. Now, after we do the fabrication, so we have to do again the chip measurements. So basically, it's kind of a verification process. So to test the chip, we have to verify we are getting the same result or not. And if there is any mistake or if there is any problem with the IC, then we again need to redesign it. So basically, we don't prefer redesigning it. So that is why it's very important that once we generate the GDS2 file, so before generating the GDS2 file, so we have to confirm that our design is all correct and whatever parameters we are putting into, so we are getting a good result. So before that, we need to verify. Now, to ease that particular process, we have to do a simulation that is called as the PVT simulation. So in the PVT, we have to do the process analysis, we have to do the voltage analysis, we have to do the temperature analysis, and apart from that one, we need to do Monte Carlo analysis. So all these four analyses are very, very important before we can send our IC for fabrication. Once we complete those simulations, once we do all the layout and post layout along with those results, then there is a chance that we will have a success rate or we will have a high yield rate after we do the chip, we can say fabricated chip will have a better yield in that case. So this verification process mostly takes around 2 to 3 weeks. So if you sum all of those, so it takes nearly about a year for the whole thing to execute. But for the designing part, it can be actually done within 2 to 3 months. So it's better if you start implementing your idea. So if your design is small, then you can complete within 3 months. If your design is a bigger one, so it may take around 5 to 6 months. So depending upon the design, it actually differs. So this is about like the flow. So if you have any queries regarding the timeline, you can let me know so that I can help you decide like what actually you can do or which type of design you can focus on. And you can actually try out some of the designs and you can actually go for the fabrication. So it all depends upon you. You have to set your timeline. So I have given you a brief timeline that how much time it will require. And if you follow the particular timeline, then you can complete your design in a very good amount of time. Right? So if you follow the timeline, you can easily complete your design. And it all depends upon how big your design is. So try to choose it wisely. Like whatever designs you're choosing, so try to choose it wisely. That's what I would suggest. Now, the next thing that I would like to discuss is understanding the VLSI design flow. So here, what I need to discuss is what is intellectual property. Now, we told you about analog IPs or digital IPs. So this IP is nothing but intellectual property. So the like in digital circuits, you might have seen that when you write a Verilog code or a VHDL code, so you just write down like say X XOR Y, or you write X and Y. So you're just naming the gate, right? XOR gate. You're naming the gate as a AND gate. But what is the process of that gate? Let's say what is the technology that has been used for that AND gate, or what is the technology that has been used for the XOR gate? So how do you decide that? So in case of a digital circuit, what we usually have is we can call upon any of the technology. So we just implement the logic and we can call upon the particular technology and we can actually implement. So there are some cells called as the standard cells. So this XOR or AND. So these are standard cells. And how do we make the standard cells? Is for a particular technology, the standard cell size will vary. So that also we'll see like what is a standard cell and how to actually create a standard cell. Now for the op-amp also you can create a standard cell. It's not that for an op-amp you cannot create. For the op-amp also, you can create a standard cell. For a comparator also, you can create a standard cell. And for, let's say, a biasing circuit also, you can create a standard cell. So it all depends upon you how you are creating. So I'll tell how to basically form a standard cell. So that will cover in the next one. Now, the advantage of the IP is that it will save a lot of time. Let's say for one of the technology, let's talk about the Global Foundries 180 nanometer technology. So for Global Foundries 180 nanometer technology, so there are some standard cells that we can use directly into our program. Okay, and let's say we can directly use the AND gate, we can directly use the XOR gate, and simply we can execute it. So that is what we actually do in analog IPs and digital IPs. So these are already predefined. Means the global foundries or any other fabrication lab, so they already have that definition that what will be the size of the particular gate, okay, what will be the shape. If there are three inputs, so what will be the size? If there are two inputs, so what will be the size? So these are all predefined. Okay, so they already have the right. So an IP can be classified into these groups. So if you classify in case of journal, so there you can call it as ASIC IPs, you can call it as analog IP, interface IP, memory, core, verification. So you can have this classification by size also, you can have this by distribution also, and by circuitous nature also, you can actually classify it, or by the form, that is a soft IP and hard IP. So in the soft and hard IP, the thing is like in the soft IP, basically we have this Verilog code or a VHDL code. So with this Verilog and VHDL code, so we just call upon the XOR or AND gates. So these are called as the soft IPs basically. Now for the hard IP, so when we do it manually, means if we have a layout of an AND gate or layout of an XOR gate, so directly if we use the layout of an XOR gate or an AND gate, so that is called as the hard IP, means we do it manually, whereas in case of a soft IP, it is already predefined and we just follow it up through a help of program. So usually whatever designs as we see now is mostly the soft IP. And if you want to create your own IP, if you want to create, let's say, a particular standard cell, or if you want to have a particular op-amp design all by yourself, then you can go for the hard IP. And if you look here by circuit nature, so there is a digital IP, AMS IP, and analog IP. So digital IP is different, analog IP is different, and AMS, that is the mixed signal. Okay, so if you go for the mixed signal, so those IPs are also different. And this table is just to show you, like, if you talk about the standard cell IPs, so those are basically used in the ASIC chips. The memory IPs, so such as the SRAM, DRAM, so you can actually design a SRAM cell, you can design a DRAM cell. Now, if you talk about the analog, then you can go for the PLL design, you can go for a DC-DC converters, you can go for a digital to analog converters, you can go for analog to digital converters, okay, and you can also design for other kind of amplifiers or comparators. So those all will come under the analog IPs. And if you go for this SerDes and physical uses, so you have to call it as a interface IP. So these IPs are very high speed IPs. Okay, these are basically used for the Ethernet or SerDes. Then there are core IPs such as the ARM processor, RISC-V processor. So nowadays you might have heard of RISC-V processors. So ARM is nothing but advanced RISC machines, right? So it is also a RISC only. So ARM or RISC, whatever you say. So these core processors, if you make, so these are called as the core IP. And there are some verification IPs. Okay, so basically this is a vector IP. Okay, so basically we use it for the verification purpose. So now let us go to the next thing, that is the inverter design and simulation. So this I'll just give a brief about this one, because again we have to come back when we will use the open source tools. So then we'll discuss about the inverter design in more elaborative way. So for the time being, let's say just understand the you can say simulation, or just understand the characteristics of an inverter, how it is. So basically in inverter we have an NMOS and a PMOS, and this is the curve that we obtain by changing the input. So if we vary the input from 0 to 2.5, so this is how the output will look like. So when you can see my input is at 0.5, so the NMOS, you can see it is in off condition, and PMOS it is in resistive condition, or you can say in a linear mode basically. And when you go for 1 volt, so NMOS in saturation, then PMOS is inactive. mode or linear mode basically, not active. So we'll call it as a linear mode basically, or triode region. And then there is a point that is at VDD by 2. So if my VDD is 2.5, so 2.5 divided by 2. So at this particular point, both my NMOS and PMOS are at saturation. So this is how the graph looks like, and this is the conditions basically, that at this particular point, what will be the status of my NMOS, what will the status of my PMOS. Now there is the layout of an inverter. So we'll see how to make the layout of an inverter. Now this is just to show that, see, we have an inverter circuit. If you do the layout just like a schematic, then it will look as the figure 1. But if you look at this, so in the figure 2, you see the polysilicon. That red one is nothing but a polysilicon layer. So this will come back when we'll do the layout. So I'll talk about this one. So you see the polysilicon. So the size of the polysilicon is small here. Whereas if you see in the first figure, so polysilicon, it's a larger, right? So this one is a large in size as compared to the figure 2. Now we don't want to have a larger polysilicon, because if we have large polysilicon, then we'll have more parasitics. So in order to reduce the parasitics, we should have small polysilicon connections, okay, or polysilicon wires, basically we can say. So that is why the part 2 of this one, so this particular figure is preferred. Now, so after this one, let's talk about the standard cell. Okay. So what is a standard cell? So standard cell means it will have a predefined size or the length. So it will have a predefined length that blocks by blocks, it will be a fixed size. So there is a rule that is called as the half DRC, because we'll use only the half part of it. Means we'll only talk about the width of those transistors, and we don't require the length. We only focus on the width. So that's why half DRC. So this is how we actually design the standard cell. So you can either go for ultra high density kind of a standard cell. You can go for a high performance standard cell. Okay. So in the high performance architecture or a high density architecture, you can see so how we can have. So for high performance, you can see we need a larger space if you want high performance. If you want high density, means you have to reduce the size. So there is a 7-track high cell and there is a 12-track. So if you want ultra high density, means you have to bring it to 6 or 7-track height. So this is how the standard cell look like, and you have a VDD and this. So we'll like I'll show you how we can put or place our power rails and all. So let's say instead of having 2 inputs, we want to have 3 inputs. Then your standard cell can look somewhat like this. So it's normally, if you see, it's a high density cell. Okay, so we are not talking about the performance basically. So it's only the density that we are talking here. So for a 3 input, so we can put up layers like this, and we can have the cell designed in this particular format. So the boundary has to be fixed. And this is the way how we can actually calculate the standard cell, like what should be the size of the standard cell. So how to calculate the height of the standard cell. So this basically depends upon these 4 parameters. So the A is nothing but the width of the PMOS and NMOS. So what will be the width of the PMOS? What will the width of the NMOS? So based on that one, we'll have the A value. Then what is the distance or the, let's say, space between the active area of the PMOS and NMOS? So that we also need to consider. Then we also need to consider the length of the polysilicon that is extend over the active layer. And finally, the half DRC distance for the polysilicon near to the PR boundary. So what will be the half DRC distance? So if we consider these all 4 parameters, so you can see if we take the width as 100 units, so we end up having the standard cell height as 270 units. So mostly what we try to do is, like if you will see here, so it's like 100 for PMOS, 100 for NMOS plus 100. So it is near to 300. So whenever you are designing, so consider the intrinsic area of a PMOS, then consider the intrinsic area of an NMOS. You add both of those plus half of the intrinsic area of both NMOS and PMOS. So that will give you the standard cell height. Okay, so that will be, let's say for PMOS is 100 units, for NMOS it's 100 units. So overall you can add to 300. Okay. So that is how we can actually have a, let's say, basic idea, like what should be the basic standard cell. Okay, so the actual method is this, where we add all these ABCDs. But if you want to have a general idea, then you can have the area of the PMOS, the area of the NMOS, and half of the sum of PMOS and NMOS. So that will give you a general idea of your standard cell. So this was about the standard cell. Now, how to place the VDD and ground. So there can be like two ways how you can actually place. So if you have, let's say, VSS or VDD, so the second figure you can see how we can place it. And if you only have VDD and ground, so this is how you can place it. So the signals will be in between the VDD and ground. So always you see there will be a VDD rail, and at the bottom it will be a ground rail. So at the top it will be VDD, at the ground will be at the bottom, and in between this VDD and ground we'll put all the signals. Okay, so that is the perspective and how we can go with the standard cell design basically. Now, so after completing this one, so the final thing that I would like to discuss is about open source tools. So which open source tools to use? So in my opinion, the best open source tools as of now for the use of analog circuit design is LT-Spice and Electric VLSI. So LT-Spice is mostly used for the simulation purpose, whereas the electric VLSI will be used for your layout purpose, for your DRC, for your LBS, and even the generation of GDS25. So basically, we can do the whole thing using the electric VLSI tool. So this is just to show that how the LT Spice tool looks like. So LT Spice tool, in that one you'll have a amplifier circuit, like you can design this amplifier circuit and you can do a simulation. So now when we use the electric software, so there we'll only plot these signals through the LT Spice tools. And next, what an electric tool does. So you can see here what actually you can do using an electric tool. So you can make a schematic, you can even write a Verilog code or a VHDL code. You can do a layout. Okay, so here you can see you can do the layout for whatever schematics you have made. And you can also see here, you can have a 3D view. Well, for the 3D view, you need to add some additional plugins. Okay, so if you add some additional plugins, then you can actually have a 3D view of the layout. So that is very, very advantageous. So whenever you're like having an architecture which you want to see in a 3D view, you can always install this particular 3D view plugin. And after you install this 3D view plugin, you can actually have a 3D look on the layout that you have made. Okay, so once you do the layout, you can actually go for the 3D view plugin and you can observe how it looks like in a 3D environment. And then there is a simulator called as IRC. Well, for our case, we are not going to use this IRC, but this is a simulator, so we need to add it separately. If you want to add, let's say you are doing some program using a Verilog code, so you can do the simulation using this IRC. So you can install this plugin as well. If you want to do detailed simulation, so you can actually add this IRC as well. So these are the basics. Okay, so these are some of the basics of you what is the flow and the timeline that you must have in order to have the analog IC design. So this was just to show you in brief all of those things. So any questions till now? After that, we will show you how to use the tools, how we can use the LT-Spice tool, how we can use the electric tool. So before going to that one, so if there is any question, please let me know.
You can speak in the mic or you can write the questions in the chat box also.
Yes, so if you have any queries, so you can just ping in the chat box. So till now, whatever whatever we have covered, right? So starting from the idea that how you are going to have a design to what is the timeline that you require for executing your design. Okay, so how to do the layout, like how much time you'll require for the layout. So all those things, we have clubbed all those things together. Okay, so you can actually go through that one. Okay, so let me just go to that timeline, which will actually help you understand this. See, this one is very important. So the main objective of this particular workshop is to help you out with the designing part. So we actually want you guys to design and fabricate. We are actually exploring this open source tool space, and we want you guys to take part in this open source competition, and like put your concepts or ideas into implementation part. So mostly the thing or the difficulty that we face is to implement our design. So many of us know how to design an op-amp or the basic comparators, but we don't know whether we can actually fabricate those or not. But we are giving you a platform where you can actually come up with an idea that op-amp, let's say two stage, three stage. So you yourself design those op-amp circuits, and then we will help you out sorting out, or we'll give you these tools. So we have already given the links for these tools. So you can use these tools in order to implement your design. So for the implementation part, like you have to do the layout. Okay, so you have to do the basic simulations that I tell you what simulations you need to do. And if you need help with the simulation part, that what are the simulations that you require, so we can help you out that okay, so these simulations are required. So for your design, you do these simulations. Now, once those simulations are done, then we will go for the next phase, that is the layout part. Like how you are doing the layout, whether you are like facing any difficulty in the layout, or let's say like whether you are able to complete the layout or not, and what are the things, let's say for example DRC, LBS, then parasitic extraction. So all these things you need to do. So those are very, very important. So we'll show you like how to do those things, how to extract these particular things. But before that, I'd like to give you 5 minutes of time to just think of it and let me know what you want, like what you are trying to do here, like what is your plan. And we are already giving you this timeline as well. And we need to complete this whole process within 3 months. So that is why we want to have, let's say, we want to observe your progress basically. And for that one, I think Alok sir, we can have a progress kind of a thing. Like I think,
Yes.
yeah. So like in the next week, like after your session, so after that, we can put up a message where students or faculty, like whoever has joined, all the participants, so they can actually tell us or give a small presentation, or they might submit a report, like just a brief report that what they are actually trying to build, basically,
Yeah.
whether they have started or not, and whether they are facing any difficulty in this one or not,
Mm.
and what kind of mentoring they need.
Yes. So today, till today, yes, in the last week, I have introduced the tools and how to install and all those things. Today, you will be doing that. So tools part is taken care. So next week, the plan is I'll describe some of the most commonly used protocol digital things that they can target. Little bit of description, because those description are all over the internet, so they can do it, but just few things that I thought that I'll just touch upon. And probably there will be another week, maybe you can add similarly the most widely used analog things, little bit touch upon if you want to do that.
Yes.
And after that we'll open for the submission, submit your design. At least the submit that substract first week, then give us the initial design, then give us the simulation results. Like that it will happen.
Okay.
And till today or after maybe 2 weeks also, still they have time. They have to continue to work. They can still start designing today itself.
Yes, yes, yes. So if they at least have the idea that what they're actually trying to do, I mean, they can do some literature review or kind of a thing.
Exactly.
Then, so that like it will be easy for them, because suddenly if they start designing, the designing itself will take a lot of time for them.
Lot of time. Correct.
So because for simulation now they won't take much time, but for the designing part, like what they actually want to build,
Correct.
so that may take time. So I'd like to request the participants that at least like you do some reviews and all, so that
Correct.
at least you can come up with an idea, and we are there to help you out. So either you do analog design or the digital design. So whatever you are doing, so at least have an idea like how you want to implement, because we are just giving you an idea how to use the tools, and like what are the things you need to do, like what are the simulations you need to carry out, and how to approach with your design. So these things we are telling you, like what should be your approach basically. So
Correct.
any
So
participants have any? Yes, sir, please. Tell.
yeah, so now today or maybe after next two till next two webinars, at least you have an abstract. You write the block diagrams, which components or which blocks will have. Then gradually start, analog designers gradually start your like schematic, and digital designers start your Verilog. That
Yes.
that would be the good thing.
Yeah, so that should be there. Yes. So because within 2 to 3 months we need to do, so that should be, because design has to be finalized first, and then only, because as I shown you the timeline, so there is still like the designing part will take a lot of time, like 1 to 2 weeks only it will take for the design to be finalized,
Yes, right.
and after
So,
that also it will take time for the layout and everything.
hmm, so there are two questions. One is from Ravi Kiran. Which IP should we, sir? We can design any IP which is existing, or yes, existing IPs are okay.
Yes, yes, existing IPs they can start with.
I mean, basically, you can complete if you haven't something existing. Like if you start really from scratch, then this 3 month is really short. So
Yes.
existing is always welcome. I mean, and that is more feasible.
Yeah.
Uh, he is again asking, can you give an idea example of what kind of IP we should work on? So in digital, simple protocols like SPI, I2C, UART, then VGA, HDMI, USB. If anyone can design a USB protocol, that would be great. And Ethernet, PCIe Express, and remember there are others also, like audio chip, like codec, uh, MP3 codec, or coder decoder, then MP4 video codec, coder decoder. So those are things. And remember, suppose if you are working on Ethernet, suppose you if you think, don't think that you have to like gigabit Ethernet. No, the basic thing you do, that is fine. Don't worry about the speed, don't worry about the megabit per second data transfer, like that. Have a functional but simple thing. If it is slow speed, that is also fine. So those are the digital things widely used. In analog, like the most of the things is the Subha Rao, the next question he asked, like DC-DC converter, buck converter, boost converter, that is
Yes.
very important. And D2A, A2D, that is very used always, everywhere that is used. That is a very useful thing. And coming back to ADC, there could be simple ADC, R2R ladder kind of thing, or it could be SAR, So if you can do a complicated A to T converter, do it. If you cannot do it, do a simple A to T converter. It may not be megabit per second. It could be a slower conversion also, lower resolution. Everything is fine. Just do a like complete workable thing that is there. And in analog, in audio video or domain, like if you can design an audio amplifier, that is really appreciated. If you can do pre-amplifier designing just before amplifier, that is also very much appreciated.
Yes, so there are actually so these are like DC-DC converter also you can start, and this can also be done. Like if you want to do only the simulation part, so that can be done using the LT Spice. Okay, so if you are trying to do a DC-DC converter, so there you need to see like what type of transistors you are going to use actually. So there, like DC-DC converter, we have to tell what type of transistor we are using. And for fabrication, you need to use some layout tools. So for layout tools, you can use the electric. And there are other tools such as the magic also, like where you can actually check for the layout part. So you can do the layout using the particular magic tool also. But like as I told you that my preference is always like electric VLSI because there you have got a lot of scope basically. So there are a lot of things in electric VLSI which you can explore. So that is why I basically like generally actually I prefer having that particular electric tool. So now when I'll explain the tool and all the usability, so then I guess it will be more clearer. But yes, of course, you can start with the DC-DC, but here we don't only focus on the simulation, but here we need to do the layout also because finally the file that we need to generate is the GDS because here we are talking about the fabrication of analog IPs. So there we need to generate a layout. We need to generate a GDS2 file. And for that one, we need to have a tool that will generate the GDS2 file. And that GDS2 file we can generate using the electric software.
So very important what Dr. Safra has told. So you have to work on the layout portion also. At least you have to start, you have to place things. The later thing, the finer details and the like the overall thing will take care, but you have to do layout. That you have to this thing. For analog, it is mask because analog layout is not automated. There is no tool that is, but electric has a lot of support to automate that. But again, some hand holding is needed. But for digital portion, the layout is also totally automated. So don't worry. But you have to run those scripts and you have to generate those things. We will guide you, but you cannot just give us the Verilog and say that you sir do it. No, you have to generate that layout in both the cases also.
Yes. So I guess that yeah. So I suppose these things are clear. So I'll just showcase the tools then, so that like you'll have an idea how you can actually use the tools. And
Exactly.
yeah, so there like you'll have an idea what exactly you can do using these tools. What are the
Mm.
things? So if you can see, okay, let me just go back
Yeah.
to this particular slide also, just to show you once again like what we can actually do with the electric software. So here, if you look at this electric software, so you can
Fine.
see what are the things we can actually do using the electric software tool. So you can see here, like it has got like schematic design also. Like you can do the schematic design starting right from the NMOS, PMOS placement to a particular layout also you can do. Then after the layout, like if you want to have a 3D view, so that can also be possible. Because in some cases, like let's say you want to have a 3D view. Let's say, for example, you have an inverter and you want to see how the inverter will actually look like what is the exact physicality. Right? 3D view means how it will look like in physical world. So that 3D view also we can get in electric, which is not possible in the other layout tools. So if you go for the other layout tool, so these things you will not be able to see. But for the electric VLSI tool, you can actually observe. Otherwise, you have to go for some CAD tools and all. Then again, integrating with those things is a bit challenging part. So that's why, in a short, I can say that using this electric tool will greatly enhance your designing part, and you can actually have a good design using this electric tools. So you have got a lot of scope, and it is the advantage is that it is open source, and moreover, you can club both LT spice with the electric. So you can actually combine this electric along with the LT spice too. So that is again another advantage that we have. So let's begin with this tool. I guess all of you have downloaded the particular software tools. So I'll just start with the basic, like I'll just give an introduction of the LT spec and then I'll just show. Okay. So LT Spice tool. So one version of this LT Spice is LT X311. So basically, it's you can use that one also or this one also. So LT Spice has got multiple versions. So now the current version will look somewhat like this. So like this one background I have added, but yeah. So what we can do in LT Spice is see here, like we can do a schematic design also. Okay, so in this schematic design, we can actually drag and drop the components. For example, let's say we have a NMOS, PMOS. Okay, so we can actually select NMOS or PMOS port. Let's say I want to design an inverter, so I can actually put a PMOS and also a NMOS, and I can create an inverter. So I can place and I can build up a circuit here, right? So I can create a circuit and then I can do the simulation. So this is one thing that I can do with the LT Spice tool, like just creating a basic schematic and doing the simulation. Now, for simulation, like I have got a lot of options, so that I need to show you. That's why I opened this one. So you can have these settings and parameters, and you can configure what type of analysis you can do. So here you can see you can do a transient analysis, AC, DC. You can do the noise. You can do DC
So
transfer.
we can't see the graph window.
Okay, okay, okay. So I think I have just shared the window. That's why. Okay, I'll just share the complete screen. So now, like the thing is, so if you want to do the simulation, so we can click on simulate and we can click on configure analysis. So here we can see a lot of different type of analysis that we can do. So we can either do a transient, we can do a AC analysis, we can do a DC sweep, noise, DC transfer, DC operating points, transient frequency response. So there are a lot of simulations that we can actually do using this Spice tool. So that is why we basically prefer this LT Spice tool. And we have got a lot of options for doing the simulations, and whatever basic simulation we want, so we can actually perform here. So if you are doing only the schematic simulation, so you can use the LT Spice tools. So it has got a lot of options, and you can actually implement bigger designs into LT Spice. Now let's go back to electric software. So in the electric software, basically, let me open that one. Okay. So before opening the electric software, so what we need to do is that we need to create a separate folder first. Okay, as you can see on my screen, so I've created a separate folder, right? So I have created a separate folder. So you can see here. So in this particular separate folder, so I have these folders put here. So this GF180 is nothing but a global foundries technology file. So this all is there CMOS. Okay, so you can see four to five different CMOS are there. So CMOS FF is there, FS is there. So we'll talk about what is the fast and slow processes, what is the typical processes. So, but this particular GF180 carries all these technologies in one folder. So this I can share with you if you want to do, like if you want to use the global foundries 180 nanometer technology. So you can actually use this folder. Now the important thing is that you should keep all the files in one folder. So whenever you are doing any kind of simulation, so this electric binary file, so you should keep this file in one folder, and that folder you can keep it in your desktop. Now, if you don't keep this one in separate folder in a desktop, then you may get some errors like permission denied or something. So you'll get those kind of errors if you don't like keep this electric binary file in a folder, like in a separate folder. If you keep this file in a C drive, then you might get some error. So it's better to create a separate folder, okay, and then you keep this electric binary file in a separate folder like I did. So I created one folder called as Fabulous. There I put this electric file, and there itself I have put this GF180 nanometer technology file. Now I want to do a program, so I created a program folder where I'll keep my programs. So now what I'll do is I'll click on this electric binary file. So no need to install this electric binary. For LT Spice, you need to install the LT Spice. But for electric binary, so you don't need to like install anything, just the Java run script that you'll require for this one. Now you just need to copy this jar file and double click on it. So when you double click on it, so then you'll get a window. So let it pop up. And meanwhile, I'll just close this LT Spice too. Okay. So now here we are with this particular electric tool. So this is how it looks like. So now the first thing that we need to do is create a file. So before that one, we need to create a new library. So just click on this new library and give a name to this new library. So let us, for example, let's say we want to create an inverter. Okay, so this I'm not creating any differential amplifier and all. So for the basic things, so I'm just going with the inverter design only. And then later on, we will discuss about the differential amplifier designs. So let us start with inverter design. So I give the name of the library as inverter. So you can write it as my library also, that is fine. So inside that my library, you can have, see in this inverter, I can like I'm just making a library for the inverter, then you can make it for, or otherwise, okay, so just let me do that one. Let's remove this one and let me. Okay, so what I'll do is just close these two and create. So let me just create a 180 GF180 nanometer library. Okay, so I want to create an inverter. So what I'll do is I'll click on this new library, and here I'm just writing INV, okay, 180. So INV 180 is the name of my library. I'm doing all those things. Or if you want to make, let's say, inverter, NAND gate, NOR gate, all those things, so you can give the name as digital 180. So it's just the library name. So it does not mean what design you're making. It's just a name given to the library that you want to access, and inside that library your files will be there. So let me create a library called as 180. Okay, so inverter 180. Now once I create this library, I need to have some cell. So what cells I will require? So first let me create a inverter cell. So I'm not going for any AND gate, NAND gate, all those things, but simply I'll create a inverter cell. So for that one, just right click, or you can go to this cell and new cell also you can click, or otherwise just right click and click on create new cell. Now in the new cell, you can see there are a lot of options, right? So here you have an option for the schematic, you have an option for icon, you have option for the layout. So this icon basically stands for the symbol. If you want to make a symbol for that one, you can use this icon. If you're going for the schematic design, select this one. For the layout, you can choose this. And if you want to write any codes, let's say Verilog or VHDL, so you can choose this VHDL or Verilog also. And if you want to directly export the netlist, so directly you can go for this netlist. So there are, you can see there are a lot of views, so you can use a lot of things. Now the default technology that we are using is MOS-CMOS. So this default technology, let it be. But later on we'll call upon the GF180. So I'll show how to call that one. So for the time being, let's just give the name as INV, in short for inverter, and let us click on OK. Now this particular window is our basic window where we'll create our inverter. So here you can see INV, and in the brackets you can see schematic. So here we are going to draw the schematic. Now for schematic, we need a NMOS and a PMOS, right? So if you can remember from the design, so we need a NMOS and a PMOS. So here, if you click on the components, so under this schematic, you'll see there are a lot of options, right? So here you have this NMOS, PMOS options. So these NMOS and PMOS, so here you can see this one is a three terminal, this one is also three terminal. So as you can see the symbol, so this is PMOS and the other one is NMOS. But we want a four terminal device. Now onto the left, you see this is a black arrow that is not here. So once you click on that one, so you get these many options. You can use a PFET, okay, you can use an NFET, you can use NPN transfer, PNP transfer. So you get a lot of options, and here also in NMOS also you got a lot of options for this. Now out of all these options, so we'll just select this NMOS first, and we'll place the NMOS somewhere here. Okay. Now remember this, there are four terminals here. Okay, we want four terminal NMOS. Whenever you go for analog design, always use four terminal NMOS and PMOS. So I place the NMOS below, and I'll place the PMOS at the top. Now once you place this one, so all, then there is one more thing to remember. So let me just zoom it up. Okay, so let's first see this one. So here you can see the PMOS. So here we have four terminals. Now the terminal that is shown here, this arrow mark. Okay, so this arrow mark is nothing but the bulk. Now near to the bulk is always the source. So this becomes the source. This is the bulk. This one is the drain, and this one is the gate. So we need to remember this one, because whenever we are designing this, we need to focus on this. And one more thing, that grid alignment. So let me just first. Okay, so let's just do one more thing. And yeah, if you want to zoom out, so you can press shift. Okay, so press shift and click, so you can zoom out. And if you want to zoom in, just you can select that one like this. So with the left click only, you can just select this one, so it will zoom in. If you want to zoom out, just press shift and then click once, you can easily zoom out of it. Now we have placed a NMOS and a PMOS. So let's bring these two nearer. Then as you can see this arrow, so the terminal near to this arrow is source. So we need this source to be at the top and the drain here in the bottom. So what we can do is we can select this one and press Control I. Now when you press Control I, a window will pop up like this. Okay. So after it pops up like this, so you can see the width and length that is mentioned as 2 and 2. So this 2 does not mean that it is a 2 micrometer or 2 millimeter. Okay, so 2 micrometer or 2 nanometer. So it just used for the scaling. Now if you keep the width as 5, it means 1 micro. So let me keep the length as 1 micro, and the width, let me keep it as a 10 micro. Sorry, 2 micro. So 5 means 1 micro. So 5 means 1 micro. So 10 means 2 micro. And I need to rotate this one, right? So in order to rotate this one, so I'll just do one thing. So I'll just mirror this one, and you can see if you mirror this, it will look like this, right? And I want it to be top and down. So what I'll do is just let me do a 180 degrees of rotation. Sorry, 270 degrees of rotation. Let's do it. Yeah. So after doing the 270 rotation, we can see it looks like this, and we will just mirror these two. Okay, so if you mirror the up and down, so it will look like this. Now if you observe this one, so we have now the source at the top. This is the bulb, and the source is at the top, and drain is at the bottom. And this is the drain of the NMOS. So now let us just connect it. Now for connecting in, so we have to be careful while connecting. Now there are some YouTube tutorials also which will show you how to connect. Okay, and you have to be careful while you're connecting. So if you have already installed the software, means you can actually try and do this one. So you have to press at this point. Okay, so at the point where you want to connect, then drag this one, and after you put it near to this NMOS, just release it. Okay, so again, what I'll do, I'll place this cursor near to the gate of the PMOS. I'll click, okay, left click, then right click. So left click, then right click, drag it. Okay, so you can drag this one. Okay? So you release it, so it will be like this. Then again, you drag it with the right click and release it. Now for the NMOS, again, you select the NMOS. Now at this particular point, you can right click and drag, and then release it. So this way you can actually make the connection. So similarly, we can do the connections for these as well. So I can do a right click, drag. Okay. Then for this one also, right click, drag, right click, drag, right click, drag. So this way I did the connection for this. Now similarly, I can do for the NMOS also. So right click, drag, right click, drag it. For this one also, right click, drag, and right click, drag. So I have done this part. Now it's very important to save your design. So you should always click on File, okay, and then you can click on Save Library as. Okay, so if you click on Save Library as, means it will save your particular library in a specific folder. So you can go to the desktop where I have kept. So you can go to the particular folder that we have created. So I've created a folder named as FAB.ULOUS. Inside that one, program. So there only I'll keep my library file. Now you can see the name of my library file. So that is INV 180, and the extension is JLib. So now I have saved this one. So I've saved my design. Okay, so here I need to give some pin numbers also. Okay, now before that one, for the NMOS, I have not chosen a size. So I'll single click on NMOS. I'll press Control and I, and here in the width, I'll write it as 5, and length also I'll write it as 5. So 5 means 1 micro. So I've kept NMOS as 1 micro, 1 micro, and the PMOS as 2 micro and 1 micro. So you can also do this. So if you go to this MIS, so you can actually put some text, right? So annotation text and all those things you can actually put here. So if you want to put some text here to represent something, that also you can put using this miscellaneous. Now, after the completion of this one, the next thing is to place the pins, right? We need to identify which one is the input pin, which one is the output pin, and what are the, let's say, for example, for this case, we are taking a VSS and a VDD. So for this, we need to create something. Now, before that one, let's say you want to have a smooth connection. So for that one, you can click here and check the grid alignment. So you have to choose the smallest grid alignment so that the drag and drop is very, very smoother. So if you want a smooth drag and drop, so always choose the grid alignment as the smallest one. And here you can also, you also have an option for the grid preference. Now, if you go for the grid preference, so here you can put as, instead of 0.5, you can put it as 0.01, so that you get a better resolution basically. Okay. So since we have selected it, so you can see here 0.01. So it is selected. So we have got a good resolution. Like whenever we will drag anything, so it will be very much smoother basically. Now for the pin, so we have to take, so here you can see one option is there for the VDD. So this circular, so this basically stands for the VDD. and this particular symbol is for the ground. So you can use these pins, or you can actually check here. So there are a lot of options actually. Here you have cell, and okay, so it's taking some time anyway. Okay. So here you can see, so there are some other pins also, like unrouted pins, universal pins. So these things also you can actually select, and from here also you can select some pins, like say for example global or partition. So there are a lot of things that you can actually do. Now for the pins, I can select this one also. Okay, so right now this size is too big, so let me just. Okay, fine. So what we can do is we can choose some pins for this. Okay, and we can have this one as the input and output. So we can do it by putting some netlist like that. Okay, so for the pins, you can just select this and we can place it over here. So this is basically pin. Okay, so here it can be an input pin or an output pin. So let us just first place this pin, and at this point we'll just drag it and connect it. Now I want to name it as an input pin, so I'll single click. Now this time, instead of pressing Control and I'll press Control E. So Control E, an export window will come like this. Here I'll write IN for input and the characteristic. So I want it to work as an input pin. So I'll select here as input, click on OK. So this will behave as a input pin. Now I want an output pin. So again, the same thing, just place the pin over here. Now for this pin, again, press Control E. Here in this case, select the characteristic as output, and let us write it as OUT. And therefore, we get it like this. So let's bring this letter somewhere here. And here, single click to select, right click, drag it, and drop it. So I've done the input output. Now similarly, I have to do for the VDD and VSS. So let me just place it over here. Okay, and this time this pin will call it as VDD pin, and this pin, let us have this as bi-directional pin. So now let's move here. So now let us just connect this one. So right click and drop it. So that is done. Now similarly, I can do for the below one also. I can place this one, press Control E, and here I'll write VSS, and I'll just keep it somewhere here. Select, right click, and drop it. That's so now I have connected all the pins. Okay, so you can see the pin connections and all. So let me just save my design here. Okay. So till now, I have created the schematic of this particular inverter circuit. So the lower one is the NMOS, the upper one is the PMOS. Okay. So I can also use the annotation text also required. So here let us just press Control I for this one. And you can also choose the text size. So let me choose for this. And the above one is the PMOS. So let me just consider that. So annotation text I'll take and I'll name it as PMOS and text size. So and below I'm just writing it a multiple of 2. So this will look somewhat like this. And yes. So I have this PMOS and NMOS. Okay. Now we have not called upon any of the technology file here, right? So we need to call upon the technology file that we are considering. So this one is GF180 so PMOS and GF180 NMOS. So now what we'll do is we'll go back to our previous folder. We'll go to this GF180 nanometer, and here you can see there are a lot of file definitions here. So here all the SSFF. So this will talk about what is SS and what is FF. So we click on this one, all underscore all the 4 T's will be there. So once we click on that one, you can see here in this particular folder. Okay, so I'm not sure whether it is see or not. So now I guess it's visible. So there you can see we are calling upon the NMOS T and PMOS T. Okay, so NMOS and PMOS. Basically, we are calling these two files. That is NMOS underscore T means it is a typical NMOS, and PMOS underscore T means it is a typical PMOS, or you can say nominal values of NMOS and PMOS. So let us open the NMOS T file so that you'll have an idea like what exactly I'm talking about. So if you open this file, you see the definition of the NMOS. So this definition is what? Okay, the circuit is called as the NMOS underscore 3P3. So that is the name of the NMOS according to the technology. So that is the name given to the NMOS. So NMOS underscore 3P3, and the connections are in this way. So whenever we are defining that particular NMOS, so it is drain, gate, source, and bulb. So let's go back to our circuit. So here what we are trying to do is, now we'll select this particular NMOS here and we'll call upon the spice definitions. So first of all, we'll do a DRC check. Okay. So once we do a DRC check, you'll see that some errors may come up or there may not be any errors. So if there is any error, so click on OK, like the one we are getting. Now you can check the error in this error window here. Okay, so there is one error found in the particular schematic. Okay, so what is that error? So that also you can see, if you go above, you can see the error, like where there is an error. Okay, so that is one thing, like if you scroll up, you will find what is the error. Now the other thing how you can get the error is go to the Explorer. Here you will find this error is this tab is there. Now if you expand this one and double click on this, you get to see that the error is somewhere here and it is called as unnecessary pin. Now the unnecessary pin, you can directly click on delete, and once you click on delete, the unnecessary pin is already deleted. And now again, if you do the DRC simulation, so you can see there are no errors found. Okay, so no window will pop up here, and here in the messages window, you'll see that 0 errors and 0 warnings. So there is no error right now. After you're done with the DRC, what we can do is we can go for the simulation spice, because here we are setting up the spice model. So we'll click on the set spice model. So click on this set spice model. Okay, so before that one, we need to select. So let's say I selected the NMOS. Then I'll go here. Okay, tools, simulation spice, and then set spice model. Now you can see here. So let us just bring this one somewhere here, or let us just delete this one, otherwise it will create some confusions. So let us just delete these two. Now you see one spice model written over here. Now similarly, we'll do for the PMOS also. We'll select this PMOS over here, go to tools, simulation, and set spice model. Now when you click on this one, so you see that set spice model. So we are going to set the spice model for the PMOS and the NMOS. Now what should be the name of this spice model? So you look at the technology file that we have. So here the name of the NMOS is NMOS 3P3. So you copy this one. Okay, and here instead of spice model, okay, so let's just press Ctrl I for the instance, and here you can just paste the NMOS 3P3, and then you apply it, click on OK, and you see this NMOS 3P3 here, and it is linked with the NMOS that we have. Now for the other one, we need to call it as PMOS. Okay, so earlier we called it as NMOS. So here just change the name that to PMOS, apply and OK. So here we are calling this PMOS here. Okay, so the above one is PMOS 3P3, the lower one is NMOS 3P3. Now you can save the design. You can again do the DRC, check the hierarchical error, and there is no error. So now we have added the technology to this one. Now we need to do the simulation for this. So how do we do the simulation? So for simulation, we need to have a test bench, right? So either what you can do is you can directly call for the simulation and invoke the LT spice, and there you can call upon any kind of simulation that you want to do there. So for the time being, let's okay. So before that one, there is one method of integrating the electric with the LT spice. So for integrating the LT spice with the electric, go to the file, go to the preferences. So this is very, very important. So So you have to go to the preferences, okay. Then you have to go to the tools, and then you have to look for the spice CDL, okay, spice/CDL. Now here what you need to do, you have to select the particular spice engine that we are trying to select. So for our case, let's select spice 3, okay. Now after doing this one, then here in the running spice, so here you have to select, okay. So I'll select this run ignore output because I'm running this simulation in spice, and here I'm calling it as spice 3, and in this case, so in this writing this, so I've written as after writing this, so run and ignore the output. Now for running the program, I have to give the location for the LT spice here, okay. And then again you have to select these two, that run probe and overwrite existing output file. So these two we need to select, and above this one we have to run the program. Now from where we are going to run the program, so that particular thing we have to show here. Now this particular location from where we'll get, so just minimize this, and here in the desktop I have this LT spice, so I'll just right click on the LT spice, and I'll click on the property. So once you click on the property, you can see the target. Okay, so the target is already done. C program files, ADI, like that, it will be written. So you have to copy this particular location. Now, after copying this particular location, you have to place it in the run. And here, remember to remove this quotation mark. So once you remove this quotation marks, okay, so once you remove this quotation mark, then you can run the program directly. If you put the quotation mark, it will not run the program directly. Now here you need to put some arguments. So let us check with the arguments. I might have saved somewhere. Let me just check once. Okay, so I think I need to check it again. Okay, so basically we need to add one argument here. So with arguments we need to put. So let me just check with that one. So for the timing, let's just click on apply and OK. So this is how we actually can integrate an LT spice with a particular electric software. Now I want to run the simulation for this one. So how I do? So I have to go to tools, then I'll go to simulation spice, and then click on write spice deck. So when you click on write spice deck, so your LT spice should open, but here I'm getting some error. Okay, so you might be getting this error. See here, the error it is showing is error opening inverter.spi. So access is denied, right? So since it is showing access is denied, so don't panic with this one. Just what you need to do is you save this particular file, and the library file is already saved there. So just close this electric file. So after closing this one, again reopen. Okay, so if such kind of error comes up, then you need to reopen the particular file. So if you reopen this particular file, and let me just open up the library. So if you reopen and then if you click, so this kind of error will not come again. So it sometimes show this kind of error because there is a permission problem sometimes. Now when you click on this, see this kind of a window will pop up. So your LT spice is opening directly. So why it is opening directly is because of this. Okay, so since we have integrated, so directly it will open up like this. Now there is one argument. Let me just quickly go through that argument where I have saved it. Okay, so there is a particular argument that we need to add to it, because if you don't add that argument, so directly the code will not be there. But yes, of course, we can just directly call upon the code as well. So there is this particular, okay, so here you'll see that. So there is a complete manual for this one. So this also, if you want, I can share with you that how we can actually call upon this. Okay, so how you can run the simulations, what are the tools, or how you can actually make use of this open source code. So everything is there in this particular manual. So you can actually go through this one. You can install the plugins as well, and you can also run it in this Linux environment. Also, you can do the same thing. So if you want to do in Windows, you can do. If you want to do in Linux, that also is possible. So I'll just check with this one. Okay, so I can find that. Okay, so anyway, so that argument I'll give you later on otherwise. Now, if you check the programs folder, okay, so there you have this SPI file, and one file you have here. So this SPI file, actually we can open it up in this particular LT Spice. Okay, so if you go to the programs, you can see that inv.spi file is generated. Now this inv.spi file we can open in a LT Spice environment. Now when you open in a LT Spice environment, you see these all notations, right? So options like this, everything written, then model of NMOS is given, level 1, PMOS level 1. So these things actually you can delete it. Okay, so these are not required. Now when you see the NMOS and PMOS, so the connections are already there, right? Output, input, VSS, VDD. So all these connections are already given. So drain, gate, source, bulb. So like that for NMOS and PMOS, both are given. Now we need to call upon the model files, right? We need to call upon the model files for the NMOS and PMOS. So how do we call upon? So for that one, we can write .lib. Okay, so we can include the library file. So .lib and the location of the file. Now here, if you see the location of this particular file, or you can say the technology. So this is the GF180 nanometer layer, right? So we can select this particular whole location. You can select, or you can select just .gf180. Okay, so directly also you can call upon this one, and whatever name we are talking about, let's say for example for this NMOS and PMOS typical, so we can call upon this CMOS underscore TT. So what we are going to do, so let's just call upon .lib, and we will give the library location as this, then slash, and after that the file name that we are including. So in this case we are including this CMOS underscore TT dot txt. So this file we are calling upon, and here we have included this particular file. Okay, so now when we include this particular file, so these two will be included in this one. Now after we do this circuit, so we need to do some simulations, right? So for the simulation we need to give some input, and based on the input we'll get some output, right? So let us give the inputs. So here what I'll do is, let's say in the command line, so here I'll write just the inputs. Okay, so here inputs. So VDD, so these connections, so this I'm basically giving a net list. Okay, so between VDD and 0, I have, let's say for example 1.8 volts, and VSS and 0, I have a DC voltage of 0. So you can either write down DC here. Okay, so DC voltage 0. Then next I want to give input. So V in is IN and 0. And here I can give any sort of input. So it can be a pulse, it can be other something. So let us use a pulse input. So in the pulse, so I can give a definition here. So here, what will be the definition of the pulse? So pulse, what will be the lower voltage? What will be the higher voltage? So all those things we need to define. So if you are giving a pulse means, let's say the low voltage is 0 and the higher voltage is 1.8. Then what is the period? So let's say you don't know what values you will write here. So for that one, what you can do, you can click on file, you can click on new schematic, Okay, let's say you don't know, so that's how like you can do. So you can just place an instant of voltage here. Okay, then you right click on this one, go to advanced and see here, okay, this pulse. So you can see the definition how you can call upon a pulse. So V1, V2, delay, okay, so rise time, fall time, then on time, period, and n number of cycles. So this is how you can actually call upon a pulse. Okay, so let's say initial value is 0, then 1.8, delay is let's say 1 nano, okay, rise time is 1 nano, and on time let us keep it as 50, okay, and time period let us keep it as 100 nano, and number of cycles let's keep it as 2. So you can see the definition. Okay, so here you can see the definition that how you will, like how you can actually call upon this pulse function. The same pulse function you can just have it here. The same pulse function you can just call it and you can place it over here. So this pulse you can see the pulse that I'm giving as an input. So now input you are giving. Now we are doing a transient analysis. So I'll just call upon transient. And for how many seconds? So let's call it for 500 nanoseconds. So I'm doing a transient analysis. And in this transient analysis, this is my input. I'm giving a pulse input. Okay. Now I want to simulate this one. So let me just close the previous one and let us just run the simulation. Okay. Now when you run the simulation, you can see now this particular simulation, these inputs and outputs. So basically what we did is we created the schematic in the electric software. We generated a .spi file. We called upon this SPI file in an LT-SPICE tool. And after calling the .spi file in the LT-SPICE tool, we gave the inputs in this particular format. Like we have given what is the VDD, what is the VSS, then what is the V input. So we are giving a pulse input to V in. Then we are doing a transient analysis for 500 nanos. Now this particular waveform window has come up. Now we can right click on this one and select the add traces. Now what are the traces we want to plot? So here we want to plot the V in and V out. So I'll select V in, then I'll select V out and I'll click on OK. So you can see here, okay. So for this, so because we took only for 2 cycles, so it is only showing for the 2 cycles. So let's just zoom in only up to this one. So you can see the inverter response. Okay, so now the green one is the V input. You can see the input here, and the blue one is the output. So this is for the technology that is 180 nanometer technology for the, okay, so GF180. So this is using the GF180 nanometer technology. So this is the response that we get for a inverter. So I suppose this is clear, like how we do the schematic using the electric software and perform the simulation in a LT-SPICE environment. So we generate the file called as the .spi file, and we use that .spi file in this particular LT-SPICE tool to observe the waveforms. Now, after observing the waveforms, let us say that we want to save the waveforms, right? We need to save the waveforms in the form of data. That also we can do. And later on, we can plot using a MATLAB software or any other software such as the Python. Okay? So using the Python matplotlib, or you can use the MATLAB software to plot these kind of waveforms. So for that one, we can go to File, and here there is an option that export data as text. So you can actually export this V in and V out data as text file, and you can plot it. So therefore, you can do this simulation like this. Okay. So up to this one, I suppose it's okay. Or if you have any questions till now, please ask me. So is there any question regarding using of electric tool and LT-SPICE?
So I just faced a query regarding the installation of electric tool. So I had downloaded the jar file that was sent in the e-notice, but it
Okay.
has few other files in it, and we don't have the direct double tap thing. So I think there is some installation process required for that.
Okay, let me just show you how to do that. Okay, so let me just pull this up. See, for electric VLSI tool, you can just search also. So electric VLSI EDA tool, directly you can search like this. Okay. So after you search this one, so you get to see there are a lot of YouTube tutorials also there. Like it will show you how to download and install. Now, if you don't want to go through that one, so let me just show you how you can set up. So there in this first link, static free software download, you click on this one. So after you click on this one, you get these kind of releases. Okay, so get JNU Electric binary release, and there is JNU Electric source release. So what you need to do, you have to click on this one, version 9.07. That is the binary release. You just click on this one. Okay. So once you click on this one, you get this electric binary 9.07 or 07.jar file. So this jar file you need to save it. That's it. Okay, so for this one, you don't need to install any kind of things. Just you need to save this jar file. That's it. Okay. I hope
Understood.
that is clear, like how to install the electric software.
Understood, sir.
Okay.
And from where can we get the PDK, the 180 nanometer PDK for global foundries?
Yeah, so that is actually with me, and I can quickly share that one as well. So let me just zip this one and share. Okay.
So, if possible, can you share the lab manual also for the electric and LT spikes?
Yeah, of course. So I'll just share these three things. Okay.
Thank you so much.
Yeah, so that like at least you can go through this, right? So please that will. So this zip file I'm sharing along with this electric manuals. So let me just put it in the message box. This- Wait, I think I will not be able to attach the files, I guess. Okay, so I think I'll share this with the e-notice, or we can do one thing. I'll just put otherwise a link.
So
Okay.
you can create a drive link and upload and share it, right?
Yes, yes, yes. So I'll do that one. So I'll create a drive link and then I'll share this. Okay.
Thanks.
So now I think it will take some time. Okay, so just give me 1 minute. Otherwise, just I'll quickly do one. Okay, just give me 2 minutes. I'll just share that link. I think I already had that one. Okay, so let me just check with this open source tools. Yeah, I think electric manual Java despise and despise tutorial. Okay, we just put this one in. I suppose you can download from this one. Okay. So I have shared this link where you will get all those tools. Okay, so here I have shared the LT Spice tool, electric tool, the Java runtime that you need to install, along with the documents. Okay, such as this one, like for example, the electric manual and the LT Spice manual. So all those things along with the GF 180 nanometers. So all those things I have shared there. So you can actually go through that one. So that will be helpful. So I suppose that is okay till now, like how to do the simulations and all. So unless you do it by yourself, so I guess that won't be that much easy, because if you do it by yourself, then only you'll understand what are the difficulties you are facing running the simulator and all those things. So I'm here just to show you that what are the capabilities of the electric tool, like what else we can do with this one. So since time is running short, so I'll be quick with this one. So this is how we do the circuit simulation. Like we first make the schematic in the electric software. We generate the inverter.spi file. So that SPI file, we can use it to run the simulation using the LT-SPICE tool. Now next, if you want to create a icon, we can just directly click on, okay, this one. So inverter, so we can right click on this. And here, what we can do is we can actually create a new instance. Okay, so we can create a new instance here. So create new cell here. Now in this particular new cell, we can do a what we can do is better to do this like cell and make it as a icon. Let's see, where is it? Okay. So otherwise directly we can do create a new cell, and in creating a new cell, like we can directly choose icon. So if you choose icon means we can actually make a symbol for this particular inverter circuit. Now let us say I want to do a layout. So for making the layout, keep the name same as your schematic. So the schematic name was INV. So for the layout also keep it same, INV only. So don't keep separate names for the layout and the schematic. Now, if you keep the same name for both, so you can see here, so altogether INV one design is there for the inverter. In this particular design, we have both schematic and the layout. So this is the schematic part of it. And if you double click on this one, so here actually we can make the layout. Now, how to do the layout? So as I have shown you in the PPT, let me just open up that PPT. So since we are running short of time, so I'll just show you what kind of layout we can make and from where you can get the tools actually for this. Yeah. So see here, so this is the inverter layout. So this inverter layout, so we are preferring this particular part. So here in this case, so we have a VDD, we have a ground, and here you can see these connections, and we have a polysilicon, right? So same thing we can do over here. So for this one, what we can do is we can go to components. Now in the components, we should know what we are going to make. Okay, so here we have an option for PMOS and NMOS. So for the NMOS here at below, so you can select this NMOS here. You can place it like this. So you have placed the NMOS here. Now, if you want to place a PMOS, select the PMOS, click it here. So you have placed the PMOS. Now, observe this one carefully that these pink lines are what? So this pink line is nothing but your polysilicon. Okay, so if you refer here, so if you put polysilicon like this, so this polysilicon layer will become very large. So we want to align in this form. So that means we need to rotate this PMOS and NMOS. So here also what we are going to do, we are going to rotate this one. So first select this particular PMOS. Okay. After that, press Control I. Okay. And here we can make a rotation of, let's say, 90 degrees. Okay. So here you can see this. Now, similarly, you can do for the NMOS also. Press Control I and rotate it to 90 degrees. Okay. Now you can connect these polysilicons all together. Okay. So you can bring this one closer and you can connect these polysilicons. Now leave some space, as because if you don't leave some space means there will not be any space for connecting the wire. So you need to give sufficient space so that you don't violate the minimum design rule. Okay, so in order to go with the minimum design rule, you need to leave some space in between. Now, again, another thing is that what is going to be the size of this PMOS and NMOS? So remember the size of PMOS. So just press Control I. So the width of the PMOS is 2 micro. So we'll put at 10. Length, we'll keep it as 5. Apply it. So this is 1 micro of length and 2 micros of width. Now, similarly, we have to do with the NMOS also. So width will keep it as 5, length will keep it as 5. So both length and width of the NMOS is 1 micro. So now after you do that one, so we have to align it properly so that we connect these two together, right? Now again, see this one, we have not connected any context here for the drain and source. So we need to put some context also here. So how do we put the context? So here you can see there are N well is there is P well, okay. So there are P active and N active is there. So active we'll connect it later on. So at present we need this P well and N well. So P well we can put it somewhere here, and for the N well we can put somewhere here, right? So this well connection. So here we can connect the VDD and ground. And for this case, like let's say we want to connect the drain and gate, so we'll place it. So drain and source we need to connect, right? So here we'll place one, and another will place on this side. Now similarly for the PMOS also we can use this P active. We'll place one here, and another will place it somewhere here. Okay. Now we need to connect these both. See, one will act as a source, another will act as a drain. Okay. Now here when we are connecting, because these two needs to be connected together so that we can connect this with this wire. Okay. In order to connect these two, we need to have a connection between the PMOS and this particular contact. Now, as we know, you can check here the size of this. So we have taken the width as 10 and length as 5. Now, similarly, we have to adjust the size of this one as well. So the X size, okay, so X size, so this one, and the Y size. So Y should be same as what we have taken for the PMOS. Okay, so this is the same size as we have taken for the PMOS. Now, similarly, here also we'll do the same thing. We'll check here. So X size will remain the same. Y will put it as 10 in order to match with the PMOS. Now it matches with the PMOS, so we'll just bring it somewhere here. Now we have to be careful while doing the layout, okay, because we need to maintain a particular minimum distance. So that's why we need to be careful. So let us, for the time being, we'll place these two a little bit further. And here, let us connect these and these together. Okay. So for that one, you need to zoom into this. Now, after zooming in, you have to connect these two, and there should be like they should be all in the same line, same space. Otherwise, it will show an error. Now, when you bring it together, so see here, if you bring this one and it is less than 3, means it will show an error. So you have to keep it at least 3, and then right click here, and you can connect this one with the PMOS like this. Now, same thing goes for the other side. So first you align this one properly. Once you have aligned this one, bring it as near as possible. Okay. Now, if it is too near, then you have to make it somewhat here. Then right click and connect it. Okay. So this is how you can connect these two together. Now, this one you can bring it further here. Okay. So once it is connected, means you can actually bring this one a little bit inside, and you can see that you can actually place it near, but always remember that the spacing should be maintained. So if you are violating the space, means some error will show here. So this text, I am not sure whether it is visible or not, the text. So it will show some text. Okay? So once you do this connection, it will show some text. And if you violate that one, so some error will show, right? Like this. So here you can see, if I'm not sure whether it is visible or not. So there it is written error. So you need to maintain a particular distance of 1. So I'm maintaining that particular distance of 1, and I'm placing this here. So now this is the PMOS that I have made. Now similarly, I have to check for the NMOS and make sure that there are like these are connected properly. Okay, so there should not be any distance in that one. So you should always try to connect it properly. Otherwise, with a small error also, it will not be working. So that is why you need to be careful when you are doing the layout. Now for the NMOS side, again, you need to zoom into this. It's better if you zoom in. So then only you can do good connection. Otherwise, there will be some errors. So let us just connect here. So let's bring this one a little bit nearer. Okay. So after we bring this one nearer, so let us just connect to right click. Okay. So select, right click, connect. Now after that one, bring this one as near as possible. So when we are bringing this one, so there is a minimum distance of 1. So up to 1 you can bring. If you bring closer or lesser than 1 means it will show an error. So you can bring at least up to 1. So here I have brought it to 1 almost. Yeah. Okay, so I have brought almost to 1. And now see, we have placed this one. Now if there is any mistake in placing this one, so it will show an error. So what you can do is you can go for tools, then check hierarchy. So you can see it is showing 2 errors, so we can check these errors. Now at the initial, like whenever you're doing the layout, so make sure that you actually check for the errors with each connection. If you don't check for each connection, then later on it is very difficult. So whenever you're doing layout, it should be like you should check after doing each placement or each connection, you should actually check the DRC for errors. Now I'm getting 2 errors. So if you click on this one, you can see one error it is showing here, another error it is showing at the different. So what you can do is that for the time being, you can just delete this one and this one also. Let's say we deleted this too, and these error files also let us just delete, so that we come to know that whether now there is an error or not. So let's save it and run the DRC. Now see, there are no DRC error. You can check the error window also. So no errors are found. So once no error is found means we have made the PMOS and NMOS correct. Okay, so we have made the PMOS and NMOS correctly. Now we need to do the remaining connections. That is, we need to connect the VDD, we need to connect the VSS. So VDD will place somewhere here, and VSS will place somewhere here. And these connections, so this poly should be connected, right? So we have to place it clearly. So now see, if we place like this means it can show an error. So what we can do, we can zoom in. See, always try to zoom in whenever you're making the layout. Always try to zoom in for a perfect connection, otherwise there will be error. Okay, so this poly should connect properly. You can bring this one here, okay, and you can see. Okay, so you can bring this close and you can see whether it is properly aligned or not. And after it is properly aligned, you can actually bring this one down here. Then you can slightly bring it another portion here. So you have to be careful while doing the layout. So what I mean to say is that you need to be very careful when you're doing the layout. So like this, you can bring this one down so that both the polysilicons are properly connected. Okay. So now we can actually connect these 2 layers. Okay. So once you connect these 2, again save it and check the DRC for errors. So there some errors it is showing. So let's check what is the error. So there spacing some error is showing. I think because we have moved it, so that is why it might be showing some errors. But it is showing an error with this particular layer. Okay. So we can actually overcome this one. So that is not that much of an issue. So for that one, what we can do is like we can actually just see here. So it has been moved, right? So since while moving, so it has come a little bit upwards. So we can adjust that one. So we can actually pull this one, put this. Okay. So I suppose now it should not show an error. Okay. So because minimum distancing we are putting as 1 this one. Okay. So minimum distance actually we can maintain. So anyways, so now I should check the DRC. So there is no error. So that is why I told that while doing the layout, you should be very careful, and always while doing the layout, make sure that this is the grid alignment. The smallest grid alignment should be 0.01, and you should zoom in to the particular layout portion, and then you should make the connection so that there is no error. Okay, so there is no misplacement. Now you can do the remaining connections. So as we are running short of time, so let's, I think we can stop here about the layout. So I'll show you what else we can do here. I'll just brief you about. So see, I told you how to do the DRC, right? So you can check the DRC for the layout. So once your layout is built, you can do the DRC check. Now I have not connected any pins here. So we also need to connect pins and all those things. So this actually takes time because the layout and schematics, so both will take time. But for any help, like say, for example, what simulations you need to do, I can help you out. I can tell you what are the simulations that you need to do. But at first, as we say that we have a deadline, right? In 3 months, you need to complete. So for that one, you need to identify your objective. Means you are designing whether an ADC or a op-amp or a DC-DC converter. So you need to identify your circuit, and for that circuit, what are the simulation required? You can let us know. Okay, so you can ask us that, sir, what are the simulations that we require, and we'll tell you what are the simulations we need and how to take the readings for those simulations using those open source tools. So as I have shared already the manual for these two, but already I think that there are a lot of YouTube videos are also available. But in between, if you face any difficulty using these tools, you can always inquire. Now, what we can do with this? So I told you we can do a 3D imaging and all those things, but right now you don't need to do that 3D plugin. But up to this one you can do. So layout, you can connect the pins, you can connect VDD and all. After that, once DRC is complete, then you can do the ERC. So in the ERC, we can actually check the wells. Okay. So checking the wells is also important. So now it will show an error because we have not connected any VDD pin and VSS pin. But we have to do this ERC check. Once this is complete, then we have to go for the NCC. Now this NCC basically provides us the LVS, that is the layout versus schematic. So here you can see schematic versus the layout views. So we have to compare both the schematic and the layout. So if there is a misconnection, then it will show some error. And if it shows an error, then we need to rectify that one. Okay, that whether our layout is matching with the circuit or not. So if our layout is not matching with the circuit, then we need to like improvise accordingly. So once this is done, so then most of our part is done. Means LVS we have done. So ERC we did. Then layout versus schematic also done. Then next thing, see here you can also do this one, floor plan and place. Okay, current cell means what? That whatever schematic you have generated, so directly also we can generate this one. Okay, we can go for the floor planning and placing thing also we can do. Then there is this routing also. So if you want to do auto stitching, okay, means automatically it will route. So there are a lot of algorithms also. Maze route is there, river route is there. So you can use these routing methods also. And if you have any clock, then you can go for the clock routing. Basically, in digital design, we have this STA and all. So those things also you can do using this clock routing. Then in the generation, you can see we can generate a pad frame. Now in the pad frame, what is basically a pad frame is like, for example, after you complete your design, now my layout will be completed. Now after my layout is complete, so I have got 4 things. One is the input, output, VDD, and VSS. So for that one, I need to create a pad frame. So either you can do it manually or you can import from the Fab Lab. Now, most of the Fab Labs, such as the eFabless, where they don't have a Fab Lab. So basically, eFabless, if you look at their website, so there what they are asking is that you do the layout, you do the designing part, and after the layout, you just put that layout into that pad frame. Means they already have that framework, just you need to put the design inside that box. Now here also what we are expecting you to do is you make up to the layout, you do this DRC analysis, you do this ERC analysis, you do this NCC analysis. That means your DRC, LBS, parasitics. So all those three you have to complete. So after you complete all those three, then you go for the pad frame. So if you want to build your own frame, then you can do. Or otherwise, let's say you're giving your design to some fab companies. Let's say you have design and you want to fabricate. So what you can do, you can give this layout to us, and we will give it for fabrication. We'll just give this design to the particular frame, and with the help of the inbuilt frame, we can easily generate all the things. So basically, all the floor planning and everything will be done. Just we need to place our design on top of it. So these are the things we can do. And here also you can see after doing the layout and let's say we are creating the pad and all. So input output pads, everything if we create it, then we can go to the file and here you can see there are a lot of options. So you can export the design into a GDS2 stream. So here this is very, very important. So here there is another important, that is the LAF is also there. But for example, like whatever we need to do, so here GDS2 is very, very important. So after you create this particular layout, okay, once you put the pad frames, when you put the input output pads, then you can go for this GDS2 stream generation. And when you click on this one, GDS2 stream, so all those things will be saved there in like in basically a text file will be there which will contain all the information of your layout, like what is the minimum size, minimum distance you have taken, what is the distance between two metal layers, what is the distance between the polysilicon and the metal. So all those informations will be there in the GDS file, and based on this GDS file only your particular fabrication will be done. So I suppose this is just a brief of what actually we can do. Okay. So and yeah, so if you want to save this, let's say image of this particular layout, so you can actually export this into PNG file. And let's say I want to save this one, so I can easily save this in the PNG format. And you can check this. So here you can see this inverter.png file is generated. So this inverter.png file, so that is nothing but your layout file. So you can see the layout. Okay, so you can either take a screenshot of the layout file or you can directly generate like this. Okay, and if you want a white background, so there are options where you can change the background image. So those things you can change using the preferences command. And finally, you can just save this particular layout or schematic. You can directly export it into a PNG file format. So that is all for today. I think we'll be exceeding time if I go on explaining the whole process. But I just wanted to give you just overhead that what we can actually do using these tools. So with these two tools, so basically the LT Spice is used mainly for the simulation purpose. So we can do a lot more simulation in LT Spice. We can call upon the library. We can do analysis, let's say for delay also we can do. And there are some analysis such as the PVD analysis. So for the process we can do, for the voltage variations we can do, for the temperature variations also we can take down the result. And there is an option for the Monte Carlo analysis. So Monte Carlo analysis also we can do using the LT Spice tool. So basically what we need to do is we need to create the design in electric software and run the simulation in our LT Spice tool. So that is what we can do. And all those layout and forming the pad and everything. So those things we can actually do in the electric tool. So any questions till now about the analog design, like how to use these tools? Already I've shared those manuals and all. So you can go through that manuals, how to use those tools. And as per the analog circuit design, so I can help you out with, let's say, what are the simulations required and how to carry out those simulations as well. So any questions? Yes, yes, yes. So we are supposed to do the layout design in 180 nanometer technology. So we need to do this layout actually, because you have a circuit. Now with that circuit, you need to do the layout also. And after layout, we need to do the post layout simulation. So for the post layout simulation, let's say I made this particular layout. I want to do the post layout simulation. So I told you we can do the DRC, we can do ERC, NCC. Now after doing that one, if you want to run the simulation, let's say you have this inverter circuit and you want to run the simulation in LT Spice, then again what you can do is you can go to simulation Spice and click on write Spice step. So when you click on this write Spice, again your LT Spice will come and a .spi file will be generated. Now that .spi file you can actually call upon in LT Spice. Okay, so that file you can call upon in LT Spice, and then again you can run the same simulations. So that is how you can run the pre and post layout simulation. Both simulations we can actually run. Both post and pre simulations we can actually run in the LT Spice. And that is what we are actually supposed to do. So let's say you made a differential amplifier, you make the schematic and you run the simulation. Let's say, for example, you are observing the gain of an amplifier, okay, or gain of an op amp. So for the gain of an op amp, you did the simulation in LT Spice, okay. So you run the simulation in LT Spice. Now, after doing the layout of that particular op amp circuit, again you have to do the simulation using the LT Spice tool, and then you have to compare the pre and post layout simulation results. That what is the variation? How much is the variation from your existing one? So if you're getting a gain, let's say 35 dBs in schematic, then what is the gain that you're getting in case of after doing the layout? So that particular gain may reduce. So that may become somewhere near about 30 or 32. So that is what we are here to observe, that after the layout, what is the effect on your design, whether it is still feasible or not. Because the files that we are going to send is, or you can say, will be your layout only. So the actual file that we will send to the Fab Lab will be your layout basically. So that's why you have to be very, very careful when you are doing the layout. You have to have that I discussed about, right, those standard cell, those IPs, that about the half DRC rule. So you have to follow that half DRC rule if you are making some standard inverter or an AND gate or an OR gate. But if you're going for an operational amplifier design, so you can fix up that PR boundary, that what should be the PR boundary for my op amp circuit, and accordingly you can do the layout. And after doing the layout, you again need to carry out these PVT analysis and all. And after doing that, finally your design will be ready. And after that, there are some things like, for example, like putting up the input output pads and all those things. So that will come after a later stage. So that for now you can skip those parts, but at least you should be able to do till the layout, because layout itself will take a lot of time. So at least up to layout you should be able to complete. And further, if you need any kind of mentoring, we'll help you out how to make these input output pads and how to connect and all those things. Yeah, so I guess that's all for today. And if there are any queries, just let me know. So are there any queries regarding the tools, or what else we can do, or how to set up your idea, or the time frame? Because time frame and all those things I have already shown you that this much time you will require. So accordingly you can plan. Yes, Girish sir, do you have any queries?
I think there is no more query, and we can close today's session.
Sure, sir. Okay, so I
Hello,
guess,
am I audible?
yes, sir, you're audible.
Am I audible?